In a previous video, I had a similar problem to this that was not 100% done correctly, so we're going to be going over a similar problem that's not mine, but was brought up by someone else, so this will be pretty cool to look at. First, we're asked what is the zero of this function in the form s is equal to z1? Well, we know that if we were given an equation where we have this h of s, the numerator right here holds our zeros, and the denominator holds our poles. And so our 0 right here is going to be the 2000 because it's the only thing in here. And then our poles are going to be the P1 and P2 because these are our poles, with the positive lower value obviously being the 200 because it's the lower of the two, and the 90,000 being the higher value because it is the higher value of the two. Next, we're asked what is the gain k and dB after putting this function in standard form. Well, in standard form, we can look at this part, the 20 log k log 10 k naught, and our k naught is going to be equal to this right here. So we need to find our k naught, and when we write this out, we're just going to say that we have a 20 log base 10, and then our k naught. For this problem, the k naught is 900 times our 0, which is 2000, divided by our poles. So we have 200 times 90,000. And then we can go ahead and cancel out some of these zeros, this 2 with this 2, and then this 90 with this 90. And this will give us a 1 over 10. So if we plug this into a calculator, we are going to get a 20 log base 10 1 over 10, which will give us a negative 20. Now in previous videos, I've only provided these two things right here. Well, what we really should be looking at is this. And both of these two parts of notes can be found in the notes linked below the like button in the description. So using these, we're going to find our d and our e. For our d, we need to find the magnitude of the transfer function at omega is equal to 2000 rads per second. Now, looking at this, we are going to use the ADB down here, and I'll do it in red. So the ADB, we're going to have 20 log base 10, then we're going to have our k naught. Well, we know our k naught is just 1 over 10. We used it earlier to solve for our k. And then we have to have a plus the z, and we know our z is going to be log with a 1 plus j r omega, that's important, 2000, divided by the 2000, which is r0. Now we're going to subtract the poles. We're going to have a minus 20 log, and then inside of here we have 1. We are going to have a plus j with our omega divided by our pole, which is 200. And then we should also, I'm running out of room here, but I'll just come down here and do minus 20 log, and then we're going to have the same thing where we have 1 plus j. We'll have our pole, which is, or I'm sorry, we're going to have our omega first, which is 2000, and then we are going to have a 90,000 on the denominator. Now this is for ADB, and so we are going to be using this right here. So when we have something that looks like for below our omega corner, so when we have something that's below our corner frequency, which is the 0, we're just going to have a 0. And also when it's at omega c, it's going to be a 0. Basically what we're saying is that when we look at this, when we have an omega c, which is our corner frequency, greater than the omega being passed in, it's going to be equal to 0. So when we look at this, this 20 log base 10 with 1 plus j, and then we have 2000 over 2000, well, we can see that our omega is equal to our corner frequency, and so this can be zeroed out. And then our omega is less than our corner frequency at this part right here, so this can also be zeroed out. And then we're just left with this And then we are also left with this. And now, looking at these two, if we plug this 20 log base 10 with 1 over 10 into our calculator, we're going to get a negative 20. Now, for this one, we can see that our omega is greater than our corner frequency. So we're going to look at this last section down here. So since it's the pole, it's going to be the negative 20. And so we will have a negative 20 here. That means when we add what we have left, we have negative 20 minus 20, which will give us a negative 40. So the answer for D should be approximately negative 40, or something around that. Now we're going to look at the phase angle, and the phase angle I will do in blue. And with the phase angle, we're going to be looking at this equation here. So also we don't need to worry about this negative 90, as well as we don't need to worry about this omega right here. Plugging these values in, we're going to have tangent negative 1, where we have our omega over our omega corner frequency, and we're looking at the z first, so we're going to have 2000 divided by 2000, and I think I have an extra 0 in here, but just to be 2000 over 2000. And then we have our poles that we have to deal with, so we have a minus tangent negative 1, where we have our 2000, which is the omega, divided by our first pole, which is 200, minus the tangent negative 1 of our omega, which is 2000, divided by our pole, which is 90,000. I did forget, but let us not forget that we actually need to also take care of the kind of constant part like we did in the first part right here. We took care of that there, and now we're going to need to take care of it in here. So in writing this out, we will have a, well, it's going to be a plus with this, because this is a 0. We're going to have tangent negative 1, and then inside of here, we are going to have a 0, and this is divided by our k, and we know our k is just 1 over 10, but tangent negative 1 of 0 is just going to be 0. So this is going to be zeroed out. Now let's look at the next thing. We can see that this is, we can rewrite this as just 1, because we have 2000 over 2000. And well, if we're looking at this, our omega is equal to omega c, which it does here. It's going to be a 45 degrees. And since we are dealing with 0 here, it's going to be a plus 45 degrees. Now we can look at the next one. And for this next one, our omega, we have at low frequencies and at high frequencies, and there's two different things. So we're going to have to test out both. Our omega here is 2000. So we're testing at the low frequency first. So we have less than or equal to 1 over 10 times our omega c, and our omega c here is 200. Well, we can see that this isn't true. So it's going to be for high frequency. Let's just test that. We have our omega. It has to be greater than or equal to 10 times 200, which it is. And since this is in the pole, it's going to be a negative 90 degrees. And we are using this for high frequency right here. Now we have a 2000 over a 90,000. So let's try the for low frequency. Our omega is 2000. We know it's less than or equal to 90,000 over 10, and we can clearly see that this holds true. So this is going to zero out as well. And then we're just left with a 45 degrees minus a 90 degrees, which will give us a negative 45 degrees. And that is the answer for this part. And that is the, I believe, most correct way, I had to look at this a lot, to actually do this Bode diagram, zero, poles, and straight line approximation stuff.